Hi, and welcome to the video on characteristics of polynomial functions. We're going to do all kinds of things with polynomial functions in this video today, so let's get going. The first thing we're going to talk about is recognizing graphs of polynomial functions. Polynomials, functions that have degrees greater than or equal to 2, so just not linear or constant functions, are graphs that have no sharp corners and they're smooth and continuous curves. So we can recognize their graphs by looking for smooth continuous curves with no sharp corners. So looking down at our example, we can cross out the ones that are not polynomial functions. So the first one is a nice smooth continuous curve. The second one is not. The third one is, and the fourth one is not. We actually know a little bit about end behavior of polynomial functions from last week's video. And we can see on the first example, the end behavior matches. It is going down to the left and down to the right. So we even know that this is an even degree polynomial. And we can see that the bottom one, the end behavior does not match. It's going up to the left and down to the right. So this is an odd degree. We know the coefficient of the top one is negative, leading coefficient, because it's pointing down, like negative x squared, or frowny face. And we know that this is also a negative leading coefficient because it looks like minus x cubed. A little bit of a reminder of what we learned in last week's videos. All right, let's keep going. Today we're also going to look about the factored forms of polynomials. We can go at some polynomials can be completely factored into a form of p of x equals a, x minus r1 to the m1, x minus r2 to the m2, etc., where a is our leading coefficient, and these x minus r's are factors of the polynomial. R's are the roots, r1, r2, etc. are all the roots, and x minus r are the linear factors associated with the roots. The powers, m sub i's, are representing the multiplicity. So let's do an example, because sometimes looking at these general forms is a little bit difficult. So let's look at the example p of x equals 2 times x minus 1 times x plus 1. So our leading coefficient is 2. And the degree of the polynomial, well, if we look at our powers of x, and if we FOILed this out and multiplied it with the most we would have is x times x would be x squared. So the degree is also 2. So the highest power would be x squared. And what are my roots? Remember, roots are also known as zeros, also known as horizontal intercepts. And this is where the output is 0. We can see them on the graph here and here. And we can look at the function and decide what they are because they're going to make that function output equal to 0. And we know about the zero product property. So we can know this first factor is going to be 0 when x equals 1. And we know the second factor is going to be 0 when x equals negative 1. Which exactly matches our roots, negative 1 and 1. Now, let's just take a moment to note that our factors tell us where our horizontal intercepts occur. If x minus a root is a factor, then r is a root. So x minus 1 is a factor, 1 is a root. X minus negative 1 is a factor, negative 1 is a root. You have to be a little bit careful about the negatives on that. Let's do another example. Here's a little bit more complicated example. We have g of x equal to x times x plus 1 squared, x minus 3 to the 4th, and x minus 1 cubed. So the first thing we're going to do is list all the roots and their multiplicities, and then we're going to go into degree, vertical intercept, and end behavior. Finally, we'll sketch a graph. So let's talk about our roots. We have 1, 2, 3, 4 factors. So we're going to have 4 unique roots. We have x equal to 0. That makes that first linear factor 0, x minus 0. We have x equal to negative 1. We have x equal to 3. And we have x equal to 1. Now, the degrees on these different linear factors tell us the multiplicities. So x equals 0 doesn't have any power, so it has multiplicity 1. Negative 1 has multiplicity 2. 3 has multiplicity 4, because that's the 4th power, and 1 has multiplicity 3. All these roots multiplicities added up would give you our degree. So this one, again, we can write it down. It had multiplicity 1. So 1 plus 2 plus 4 plus 3, that's equal to 7, 8, 10. So our degree is equal to 10. And another way to think about this is if you were multiplying this all out, which you do not need to do, but the highest power you would get a squared from this one, a fourth from this one, a cubed from this one, all that times an x. You add up all those exponents and you would get 10. That's my answer to A. That's my answer to B. They want us to find the vertical intercept. To find the vertical intercept of any function, whether it be a polynomial or else, otherwise, you just find the function evaluated at 0 because the vertical intercept is going to occur when you're neither left nor right. So you're at x equal to 0. So we're going to do g of 0, which in this one is going to be 0 times 0 plus 1 squared times 0 minus 3 to the 4th times 0 minus 1 cubed. But since we have this 0 factor here, the whole thing's just going to be equal to 0. So our vertical intercept is 0, 0. And what is the end behavior of our graph? Well, we know that. We know it's an even degree, right? Because it's 10. My leading coefficient is 1, so positive leading coefficient. So we know in our head it's going to look something like x squared. So our end behavior is going to be up to the left and right. And finally, we want to sketch a good enough graph by hand. So what is a good enough graph? It means you don't need to worry about scale. We just want to have all the different features of the polynomial on the graph. So I'm just going to draw a graph, and I'm going to put all my zeros on it. So I have x equal to 0, 0, so that's 1 point. We have negative 1. We have 1, and we have 3. We know it goes up to the left and right. I'm going to sneeze. Hang on. Excuse me. It goes up to the left and right. So we know at the end it's going to do this. And we know odd multiplicities are going to cross, and even multiplicities are going to touch. So x equal to negative 1 is a multiplicity 2. So that means it's going to just come back down and go up. And then we're going to cross at our multiplicity 1. We have a multiplicity 3 at 1, so we're going to cross, and then we're going to come back down and touch. Right. This is a little more than we usually do in this class, a little bit more. But just remember, even multiplicities, 2, 4, 6, etc., come and go on the same way, just like x squared, and odd multiplicities cross through the 0. So there is my good enough graph. It would be a good time right now if you want to go into Desmos and go grab the graphing calculator and look at it. That'd be a great thing to do. So that last problem was given to us in factored form, which made it pretty easy to find the zeros and roots because we already had all the linear factors. What happens if we don't have it in factored form? Well, that means we have to factor it. So let's go through this example. The first thing we're going to do with our f of t is we're going to factor it. Now, it might have been a little while since you factored a polynomial with 4 terms in it. And there's one method we have, and it's called factoring by grouping. And if this is rusty to you, there's videos on this in the helpful videos section. But you can also just Google factoring by grouping and watch a YouTube video about it too. So we're going to set this equal to 0 because we want to know the output is 0. We're going to factor it by grouping. So we make, the first thing we're going to do is we're going to rewrite this as an equation. T cubed plus 2t squared plus negative 9t plus negative 18 equals 0. So I rewrote that as an equation. And I also, something that really helps with this is if you write all the subtracts as plus negatives, then you're not going to make a negative sign mistake when you do some factoring. And then I group the first 2 terms together, and I group the last 2 terms together. And then I factor the greatest common factor out of the first group, which is going to be t squared. And it leaves behind a t to make 2 cubed and a plus 2 to make 2t squared. and I factor out the greatest common factor out of the second group, which is going to be -9, and that leaves behind a t plus 2, which is nice. So now I have two terms, and they both have the common factor t plus 2, so I factor t plus 2 out of that. The first group leaves behind my t squared, and the second group leaves behind my -9. All right, we keep going. Let's keep factoring. This is totally factored, t plus 2. T squared minus 9 is a difference of squares, so that factors as t plus 3, t minus 3. We can also think about what two numbers multiply to -9 and add to 0. And now we have a fully factored form of our f of t. So now we're going to list their zeros and their multiplicities. So that's part B. We have t equals -2 as 1, 0, multiplicity 1. T equals -3, and t equals 3, and they all have multiplicity 1. What is the degree of the polynomial? Well, it's a degree 3 polynomial. And what is the leading coefficient? It's a 1. 3 is the degree. Hang on. Leading coefficient is 1. What else did it want me to ask? And give the end behavior. We're not going to use formal notation, so just give the end behavior. This is something I've changed. I'll change that in the notes. And so the end behavior, let's see, we have an odd degree polynomial. It's got a positive leading coefficient, so it's going to look like x cubed. So the end behavior is down to the left and up to the right. And the last thing we needed to do was do a good enough sketch of this. So here's one of my zeros, -2, another one, -3, and the last one is at 3. I didn't find the vertical intercept, but I'm actually just going to do that really quick. Let's quickly find the vertical intercept of this function. So let's just find f of 0. It usually doesn't take very long to do. F of 0 is going to be 0 plus 0 minus 18. All right, so we know f of 0 is -18. So down here, I'll just label that -18. And we have some points here. We know it's going to behave like x cubed, so it's going up to the right and down to the left, and all the zeros have multiplicity 1, so they're all going to cross over. So cross, come down, hit that, come back up and cross through. And there's my graph. All right, let's look at another example. This time we're just going to look at it from a graph. We're not even going to give you the function. Let's look at our graph and see what we can discover here. The first thing we're going to look at is finding all the zeros and their multiplicity. Well, I see a 0 here, I see one here, and I see one here. So that's x equals -3, x equals -1, and x equal to 4. The x equal to -3 is definitely going to have multiplicity 2, because it comes back and goes, it doesn't cross, it goes back the same direction. -1 is going to have multiplicity 1, because it's just crossing straight through. And when you see it level out like that, it's going to have a higher odd multiplicity. That's going to be like multiplicity 3 or higher, so I'll just say multiplicity 3. All right, let's look at the vertical intercept. It's right here. And our scale looks like it's going by 40, 40, 80, 120. So over 0, down 120. Is this polynomial even or odd, and does it have a positive or negative leading coefficient? Well, we ignore the middle parts, and we just look at the end behavior. It's matching end behavior, so we know that it's even. And it's going up, so we know that it's positive. What's the least degree of this polynomial? Well, we have to have multiplicity 2 and 1 and 3, which adds to 6. That's even. So the least degree would be 6. And a possible function would be, let's call it p of x equals a. We don't know what that is. We need x minus -3 squared, x minus -1 power, x minus 4 cubed. to match all of our possible zeros. Let's simplify that a bit. So P of x equals a times x plus 3 squared, x plus 1, x minus 4 cubed. And now the way we can find a is we can use this information here about the vertical intercept. If we plug in 0, we need to get out negative 120. So P of 0 is equal to a. 0 plus 3 squared is just 3 squared. 0 plus 1 is just 1. 0 minus 4 is negative 4 cubed. So, and this is all equal to negative 120. So it's a times 9 times 1 times negative 4 is 16 times negative 4 is negative 64. Almost there. I wonder what 9 times negative 64 is. What is 9 times negative 64?
That would be negative 576.
Thank you, Siri. So a equals negative 5, sorry. Let's just erase that. So negative 576a equals negative 120. So a is negative 120 or negative 576. I wonder if that divides evenly. How many times does 120 go into 576? There's no way.
I found this on the web.
Okay, yeah, that doesn't. So we'll just leave that as 120 over 576. So let's see, 2 would go into both of those. 60 and 2 and set 8 and 3. Yuck. That might be it. 60 over 283. Why would I pick that? It's terrible. All right, well, that's my leading coefficient. So that's a possible function for that graph. All right, and now the last example we're going to do is we're going to write a function given a bunch of information about it. So we're going to write a function for a polynomial of degree 5 with roots of multiplicity 2 at t equals 3 and t equals 1, and a root of multiplicity 1 at t equals negative 3, has a vertical intercept of 0, 9. All right, so let's give this a try. P of x equals a, our leading coefficient. So we know it has a root of multiplicity 2 at 3. Oh, it says t, so let's use t. T minus 3 squared, t minus 1 squared, t plus 3, just to the first power, because it multiplies 1, as a vertical intercept of 0, 9. So p of 0 equals 9. All right, so, and we know it has a degree 5. That's exactly right. So 2, 4, 5. Perfect. So now we just need to plug in p of 0 and see if we can figure out what a is equal to. So p of 0 equals a times negative 3 squared, negative 1 squared, 3, all equal to 9. A times 9 times 1 times 3 equals 9. 27a equals 9, so a equals 9 over 27, which is a third. So my polynomial, p of x, equals 1/3 t minus 3 squared, t minus 1 squared, t plus 3. And now the last thing we're supposed to do is sketch this function. Oh, I guess I was supposed to call it g of t. Wow, I am just all over the place with my variables here. Sorry about that. Let's fix that. P of t. So let's sketch. We know it has a double root at 3, a double root at 1, a single root of negative 3. It has a positive leading coefficient. It has an odd degree. So we know it's going to look like that. So we're going to come up here and single root here, double root here, and double root there. So there is the sketch of our graph. All right, that's it for this video.